Welcome to Let's Get to the Marks, going through the A-level chemistry paper 2, organic and physical chemistry. Sorry there, just checking my mic was on. Yeah, going through the 2024 paper 2 for AQA A-level chemistry. It's the organic and physical. You got 2 hours. Woo, 11 questions, quite a lot for a paper. Let's go. Let's get into it. So don't forget at the start of each question, press pause on the video. You might want to listen to me read out the stem, but then press pause on the video, grab a pen, grab a paper, grab your calculator and have a go. All right, I'm going through the questions. So question one, propanone reacts with bromine in alkaline conditions. And we have the equation here, CH3COCH3 plus Br2 plus OH minus goes to CH3COCH2 Br2 plus Br minus plus H2O. The rate equation for this reaction is rate equals K, and then we have propanone and hydroxide ion concentration in the rate equation. Sketch a graph on the axis provided to show how at constant temperature the concentration of bromine changes during this reaction. So why don't you pause the video, grab a bit of paper, sketch a line, and then unpause and see if you got it right. All right, I'm going to go through it. So at first we might think, oh yeah, like most reactions where the reactants are important, where they're part of the rate equation. What would happen is initially when the reactants are at highest, the reaction rate would be fastest. So we would see the concentration of the propanone decrease rapidly at first, and then as there are less, we'd expect the bromine particles to decrease rapidly at first, and then as there are less bromine particles available to react, there's less probability of a collision, and so we would expect to see this kind of curve. Like over time, the reaction gets slower, or the rate of reaction gets slower, and you can work that out from the gradient. However, because bromine here is not in the rate equation, then it is zero order with respect to the reaction. And what that means is that the rate of the reaction is not dependent on bromine and it doesn't change. So essentially, regardless of how much bromine there is, what the concentration is, as it goes down over time, it does not affect the rate of reaction. And we know that because it's not in the rate equation. And this is the sketch for concentration against time for a zero order reaction. So the gradient stays the same all the way down, which means the rate, the concentration over time is staying the same all the way down. It's zero order. Okay, that should get you a mark if you got it. Well done. And let's move on. Oh, 5 marks. That's quite a lot for a question on your second part of the paper. 1.2. Table 1 shows the initial rate of this reaction for experiments using different mixtures containing propanone, bromine, and hydroxide ions. Experiment 1, experiment 2, experiment 3. And you can see what they've done. With each experiment, they've changed one of the 3 reactants and they've done the initial rate. Okay, complete table 1. Use data from experiment 1 to calculate the rate constant K for this reaction. Give the units for the rate constant. So possibly what I'm going to do first of all is use data from experiment 1 to calculate the rates constant K for this reaction. Okay, so you can see I've written out the equation here. So rate equals K. We've got the propanoic acid, propanone, not propanoic acid. It's a ketone, propanone concentration and the hydroxide ion concentration. And we want to find K. So what do we want to do here? We want to rearrange this. So this is where you get to practice your rearranging skills. And in order to isolate K, we're going to divide the rate by the propanone times the hydroxide. So we're going to go rate. And now all we want to do, that is going to rearrange to get K. Now we just want to substitute the numbers in. So we're going to substitute these in to work out K. So 2.75 times 10 to the 11 over 1.5 times 10 to the minus 2. And that is the propanone concentration multiplied by 2.5 times 10 to the minus 2 is the hydroxide concentration. Now we don't need to include the bromine because it is not obviously in the rate equation. So some of you might be able to just whack that and keep it all in your calculator. But if you find that difficult, what I suggest you do is you do the 1.5 times 10 to the minus 2 times 2.5 times 10 to the minus 2 first. And what you'll get if you do that is 2.75 times 10 to the 11 over 0.000375. And if we blah, bloop that in the calculator, you're going to get like whatever that is. Yeah. That is pretty disgusting, the amount of zeros. I wouldn't be surprised if I got that wrong. So that is like 7.0 Oh my gosh. That's just disgusting. Let's write that instead as 7.3 times 10 to the minus 8 because there's like 8 zeros in front. I hope I've done enough zeros. I'm not even going to count. It's making my eyes hurt. Right. So how many marks would we have got so far? Well, we've used the data in the experiment to calculate the rate constant. So that is going to be at least two of the marks for that middle bit there. Possibly three, and then we need to complete the table and we need to give the units for the rate constant. Now I'm going to show you how to work out the units for the rate constant. So our rate constant is 7.3 times 10 to the minus 8. Now how do we work the units out for this? So this is a little bit that comes up in every single exam. You can be guaranteed you're going to be asked to do the units in your exam, and this is what you do. You're going to say, well, rate is in, you can see the units, they're right up here, right? So rate is in mole, dm, oh my gosh, minus 3, s minus 1. And that's over the top of mole dm minus 3 and mole dm minus 3, over the top of these two, right? So this is how we're going to work the units out. And I'm going to show you how I do it. There's actually quite a few ways to do this. So, and I vary my ways depending on which walkthrough I'm doing, because just like a bit of variation. So what I do is I add these all up, add up whatever you've got over here, and then just subtract from the top what's on the bottom. So what do I mean by that? Well, it's going to be mole dm, oh my days, minus 3. I think I've got this pen on a bit of a fat one. No, did it? And then I'm going to subtract from that. I'm going to add these together. So I'm going to take away from that mole to the 2 to the dm minus 6. And when I do that, you're going to get mole minus mole 2 is mole to the minus 1, because you've gone mole minus mole 2, mole to the minus 1. Then I'm going to go dm minus 3 minus minus 6. What do you get if you get minus, so I'm basically going to go minus 3 minus minus 6. And of course, that's going to make a plus. So I'm technically adding 3 to minus 6. So what I'm going to get is dm to the minus 3. And then the s to the minus 1, well, s to the minus 1 minus nothing. We're not taking anything away from it. So it's just mole to the minus 1, dm to the minus 3, s to the minus 1. And they are your units. So we're going to give ourselves a tick for that. Now I need to get a mark for each of these. And what I'm going to do here, guys, there's two ways to do it. So look, we could bash these into the rate equation and rearrange to find hydroxide ions, right? Because we now know K is 7.3 times 10 to the minus 8. We now know what the propanone is here, and we know what the initial rate of reaction is here. So we can whack that in and we can find the hydroxide ions. But there's a simpler way. If you check out this equation, what order are hydroxide ions? Well, they're going to be first order. Okay, and you know that because there's nothing outside the brackets. If there was a little 2 outside the brackets, there'd be second order. But these are first order. So what does this mean? This means that whatever you do to the hydroxide ions, you do to the initial rate, or whatever's happened to the initial rate tells you what's happened to the hydroxide ions. So when we go over here and we look, they haven't changed the only other reagent that will affect the rate. Okay, so that's in the rate equation. They haven't changed that. So any impact on this initial rate, and we can see something has happened to it. It looks like it's increased by how much, we'll find out in a second. That has all been caused by the hydroxide ions, and it's first order. So whatever's happened to that has happened to this. So all I need to do, and this is easier than plugging it all back into the rate equation, which you could do, is just find out what's happened to this. So I want to do 8.25 times 10 to the minus 11 divided by 2.75. And what is that going to give me? Multiplied by 3 times from there to there. And therefore, what could have caused that? Well, it wasn't the propanone. It's definitely not the bromine because it's 0 order. It's not the propanone because it stayed the same. So this must have tripled as well. So you're going to do 2.5 times 10 to the minus 2. You're also going to multiply that by 3, and you're going to get 7 1.50 times 10 to the minus 2. Now that's going to get you another mark. And then we're going to look down here at experiment 3, and we're going to say, well, what has happened to the rate? Well, let's check it out, check it out, check it out now. So what have they done with all of these? What has happened? We're at 8.25 times 10 to the minus 11. It doesn't matter what's happened to the bromine, so we can forget about the bromine. If you want, you could put a fat line through the bromine and say, right, I'm not interested, because that is zero order. It has no effect on the rate. So we just want to look like, okay, what has happened here to the propanone? Well, it was 1.5 times 10 to the minus 2. So let's see what's happened to the propanone. Well, we're going to divide 3 point, oh no, we're going to divide, it's gone down, hasn't it? Look, it's to the minus 3. So the propanone has got less. So it's gone from 1.5 times 10 to the minus 2. Now I want to divide that by 3.75 times 10 to the minus 3. What a bummer. Let's do that. 1.50 times 10 to the minus 2 divided by 3.75 times 10 to the minus 3. And that tells me it's got 4 times less. So that is 4 times less. So that means that compared to the initial rate of 2.75 times 10 to the minus 11, my first effect is that this has been divided by 4. So the initial rate will have also gone down by 4. So let's put it in as 2.75 times 10 to the minus 11, and let's divide it by 4. And that tells me that it should be 6.875 times 10 to the minus 12. So if this also here goes down by 4, divided by 4, and that's because that's first order. So if that's divided by 4, then this has to be divided by 4. Then it would go to 6.875 whoop, times 10 to the minus 12. Now, that's not my final answer. If I put that, I'm not going to get the mark. Why is that? Because I haven't looked at what's happened to this. What's happened to this? Just to confuse things even more, they've increased this. How much have they increased it by? Well, this is to the minus 1 and that's to the minus 2. So I need to divide that by that to find out how much they've increased it. I believe they've increased it by 4. So we're just going to be going back, but let me just double bubble check that. So 1 times 10 to the minus 1 divided by 2.50 times 10 to the minus 2 equals 4. What a bummer. They divided by 4 and times by 4. So we're actually going to have the same rate. So what they've done with this one, from here to here, they have times by 4. So I know I divided by 4, but I need to go ahead and times that by 4. And guess what? Divide by 4 times by 4, it's going to take us back to 2.75 times 10 to the minus 11. And there we go. That is going to be our last mark of that. Now, that was a bit of a brutal opening to this test paper, but that's a 5 marker. Let's move on and do the rest of this question. Okay, so we have the last couple of bits of this question. 1.3, figure 1 shows an incomplete mechanism for this reaction. We have propanone, we have a hydroxide ion, we have step 1. Okay. Then we have step 2. You can see bromine, a pair of electrons going from that double bond to the bromine, and that is step 2. Complete the mechanism in figure 1 by adding 4 curly arrows and any relevant lone pairs of electrons. That's 4 marks. Let's go. Pause the video, scribble it down on paper, then unpause and see if you got it right. Okay, so I'm going to go through what we got to do here. Let me pick another color. Let's go pink because we love it. Oh, maybe not. All right, let's forget about that. Right, let's go. So what we want to do is, first of all, look at step 1. Now, how do you work out what's gone on? Check this out. Focus on that. What is the difference between that part initially and after, before and after? That's what you want to do. So hopefully you've spotted something has gone on here. Between the COO has gone to CO, and that has gone minus. So what's actually happened here is a pair of electrons have gone here from the double bond to there, and that is going to make that have a lone pair and be negative. Lovely. Something else has happened. This hydroxide ion has bonded to the hydrogen. Now, what group is hydrogen in? Well, it's technically got 1 electron. It's got 1 electron in the 1s orbital. It can't already have a full 1s orbital here and then accept another electron from the hydroxide ion, or the pair of electrons from that. That would then make it have a 1s2 and a 2s2. It can't have that. It can only have two electrons in the outer shell in the old GCSE ring system. So hydrogen is essentially a group 1 element. It can only have one bond, one covalent bond, which means this needs to split. And what's going to happen there? Well, this, we can look again. What's the difference? Look there, look here, a double bond has formed. And so that has happened because the hydrogen has donated its pair of electrons there, like that. That's the worst curly arrow in the history of mankind, but from there to there, and that's what's given us that double bond. So what we've got going on is two curly arrows, and really that should be a lone pair there, because that gained a little lone pair, that oxygen, and gave it a negative charge. Now let's go down here and see what's the difference over here. Again, we want to focus on what the difference is. Check it out now. Check it out now, right? So the double bond has reformed. So we just got to reverse that process. We want to show that lone pair, and we want to show that lone pair is reform. Oh my gosh, I can't draw a circle. We want to show that reforming, right? So that is going to reform that double bond. Now, this here has gone single again, and it's gone single from double. So what we need to do is, well, we don't need to show that because that has been shown. But bromine's in group 7, a bit like hydrogen in group 1, it can only have one covalent bond at any one time. Therefore, as a covalent bond is forming here, this bad boy must break. So that's what we want to show there. And there's one more lone pair to draw on, and I guess you can guess where it is. The bromine is negative, but it has a lone pair. And there we go. We've got 1, 2, 3, 4 curly arrows, and they told us to do 4 curly arrows in any relevant lone pairs of electrons. We've got 1, 2, 3 lone pairs. So that is going to get you 4 marks, which is quite nice. Use evidence from the rate equation to explain why step 1 is the rate determining step. So why is this the rate determining step and not step 2? If you remember our rate equation, I'm going to type it out for you. Remember our rate equation, as you can see here, bromine does not appear in the rate equation. So that immediately puts us off that. The slow rate determining step will feature all the reactants in the rate equation. Well, it features propanone and hydroxide ions. So for life, let's write that again. Okay, so both reactants in step 1 appear in the rate equation in the correct amounts as shown by the rate equation. Oh my gosh, that was just disgusting. Oh, doing these videos is so long because my fat fingers are so bad at typing. But there we go. That's the end of that question, folks.
You're still here? It's over.
Welcome to Let's Get to the Marks. Going through a little question on equilibrium. Okay, let's go. This question is about equilibrium. You can see we have an equation here, 2pAq plus Q aqueous. Reversible symbol goes to R aqueous plus 3S aqueous. A 25 centimeter cube sample of solution P is added to a 20 centimeter cube sample of solution Q. The mixture is allowed to reach equilibrium. The amounts in the equilibrium mixture are P is 0.0145, Q is 0.0275, R is 0.0115 moles, and S is 0.0345 moles. Calculate, can't even speak properly. Let's try that again. Calculate the amount in moles of P before the reaction with Q. Use your answer to calculate the concentration in moles per decimeter of P in the initial 25 centimeter cube sample. This is worth 2 marks. Why don't you pause the video, grab your pen, grab your calculator, have a go, and then I'll go through the explanation. What I've done when you get equilibria questions, you could do this little table and you write ICE, ICE. I stands for initial, C stands for change, and E stands for equilibrium. Okay, so what I've done here, I've written in the equilibrium moles. So we have initial, change, equilibria. I put 0.0145 of P, 0.0275 of Q, 0.0115 of R, and 0.0345 of S. Now, what we have to appreciate is that we don't know the initial amounts of P and Q. They were the reactants. But of course, in a reaction, you have 0 of each of the products initially. So we know that R and S was 0. And then from that, we know that if you've gone from 0 to 0.0345, we know what the change is for each of these two. So we know for S that it changed by 0.0345, and we know for R it changed by 0.0115. So how do we work out what the change is for P and Q and therefore work out the initials? Well, this is where you have to look at the coefficients. And if we look at R, let's just take R up here. R P has a coefficient there of 2. So I know that it will change. If R changed by 0.0115, then P changed by double. So if I double that, I'm going to be able to work out what that changed by. And it's going to be by 0.0230 because you're going to times that by 2 to get there. Okay, now if S changed by 0.0345, I could work it out. I could divide that by 3 to find out what Q changed for. But guess what? As it's 3-to-1 with S, you also can see that, look, R is 3 times smaller than S, of course, because it's 3-to-1. So I can just go, well, R and Q are in a 1-to-1 relationship. So Q changed by 0.0115. Sure, I longed out that explanation. But essentially, they should all match their coefficients. And that means if I want to find out how much P was at the start, well, at equilibrium, there's 0.0145. It changed from the start by 0.230, so it must have gone down by 0.230. All I've got to do is add these together. So there we go. And now I know the moles of P at the start. That's going to get me one of the marks. Now I need to calculate the concentration of P in the initial 25 centimeter sample. Well, guess what? When you're doing conc, we can just do N over C times V. And I now know the moles, so I know it's 0.0375. Guess what? We're looking at a 25 centimeter cubed. So I want to do N over volume equals conc. Here's the problem. The volume's in centimeter cubed. You know what to do. Divide it by 1,000. If you do 25 over 1,000, you're going to get 0.025 decimeters. And if we do that, divided by 0.025, we're going to get a concentration of 1.5 mole per decimeter, and the moles of P were 0.0375. And there we go. So just to show you, 25 over 1,000, that's what I did to change the centimeters here into decimeters. Okay, so that's going to get us all of the marks for that part of the question. Let's move on. Now that was 2.1, we're down to 2.2. Give the expression for the equilibrium constant Kc, calculate the value of Kc, and deduce the units. Actually, let me go up here and work it out where I have the moles. I'm going to work out the value of Kc using this. So, and I'm going to do it here, and it's worth 4 marks. So just bear with me because I've got to do it over here. All right, nice one, folks. Let's go, let's go, let's go, let's go, let's go, let's go. Right, so first up, I'm going to write out the expression. Remember, for any of these constants, whether it's Ka, Kc, Kp, we want to do products over reactants. And there you go. Now I just need to plug those old numbers in. Okay, so here we got the numbers 0.0115. Don't know why I keep adding extra noughts when I verbalize. Times 0.0345 to the power of 3 divided by 0.0145 to the power of 2 times 0.0275. Now, a lot of people will make mistakes on entering this in their calculator and they pass that up. You need to be really confident that either every time you put these calculations into your calculator, you know how to use your scientific calculator and get the correct result. If you're not getting the correct result, then you need to break these individual pieces down, and you need to break those down and do them separately and then combine it all at the end. So what I suggest you do here, by the way, if we do this, we're not going to get all of the marks because this is moles. That square bracket means concentration. So of course, I need to divide everything that's in this expression by 0.045. And why 0.045? Well, there's a total volume of 45 centimeter cubed. And if we divide that by 1,000, we want to get 0.045, and that is going to be decimeters. So I need the concentrations of these bad boys. So let's just assume this is 0.045. Now, you need to do that, or say for this one, 0.0345 to the power of 3. You need to divide it by 0.045 before you go to the power of 3. So don't do 0.0345 to the power of 3 divided by 0.045. Don't do that, guys. Just because in your scientific calculator, it'll all get mashed up. So some people would prefer, let's just go through, do these individually, and then you can simplify again and again and again. Kc that we're calculating. So now what we need to do is work out the units of Kc. So we're going to get a mark for writing out the expression. We're going to get a mark for plugging all the numbers in and remembering to do that. Divide by 0.045. If you forget, you're going to lose a mark there. So we're going to get a mark then for the 1.8144, and then the final mark is for our units. Now, how do we work out the units? Well, technically, you've got mole per dm. This is what you've got, guys. So I'm just going to write it all out for you. At the bottom of the equation, we've got mole per dm, right? And that is to the power of 2. And then you've got times mole dm minus 3. So if I add those all up at the bottom, what I find I've got is mole to the 3, dm to the minus 9, and that's on the bottom. Now, if I look at the top, I've got mole per dm minus 3 plus mole per dm minus 3 to the power of 3. So I've got 4 of them. So I'm going to end up with this, mole 4 dm minus 12. Now, what I do is I take the bottom from the top, and that gives me my units. So there's more than one way to skin a cat, but this is just the way that I do it. So what I'm going to do here, guys, is write minus 12, take away mole to the 3, dm minus 9. And what's going to happen here is you're going to go mole 4, take away mole 3 equals mole. Oh, this isn't, I forgot, we're not on the right question. Okay, so that means that the units are just mole to the 1, so we just write mole. And then how do we work out the dm? Dm minus 12 minus minus 9. So essentially a minus minus becomes a plus. So if you go minus 12 minus minus 9, you get plus 9. So you're going to get dm minus 3. And that is your units. And here we go. That is the 4th mark. Now, if you can make any sense of that, make sure you hit the like, share, subscribe, all that business. Let me move on and finish the rest of the question. Explain why the amount of S increases when water is added to the equilibrium mixture. So it asks, the question just asked us, basically, if someone adds water to this equilibrium, why do we get more S? Or what happens to the concentration of S? Well, because you've got a concentration of 3 moles on here and 4 moles on here, if you dilute everything, then Le Chatelier is principle. The reversible reaction, I can't even speak, is going to try and oppose the change, and it will shift to the right to try and increase the number of particles and therefore try and increase the concentration because you've diluted it. So the answer is we will get more S, and I'm going to go write that down here, where it's actually supposed to be. The amount of S increases. So the amount of S increases as diluting the mixture means the equilibrium position shifts to the side with most particles to try and oppose the change. Right, so you basically, well, the amount of S increases as diluting the mixture lowers concentration, or I'm extending it a little bit. So the amount of S increases as diluting the mixture lowers the concentration of the particles, means the equilibrium position shifts to the side with the most particles to try and oppose the change. This is the right hand side. Bosh. OMG. Look at that nasty question.
You're still here? It's over.
This question is about hydrocarbons. Icosane C20H42 can be cracked by heating to 700 Kelvin in the presence of a catalyst. The products are an aromatic hydrocarbon C8H10, an alkane C6H14, and another alkane. Okay. Complete the equation for this reaction. Give a suitable catalyst for this reaction. I'm a little bit nuts because my internet's busted out twice at the moment. So hopefully it's going to hold it together this time. It's worth 2 marks. Pause the video, have a go, or I'm going to go through the answers. So what you got to do here, you basically, people, you just need to first of all work out how many carbons and hydrogens are going here. How can we do that? Well, what we can do, and I'm going to type this bad boy out, we can go C20. Okay, let's get the caps lock on, baby. We can go C20H42, and then we want to minus, not minus 0, we want to minus C8H10, and I'm also going to minus the C6H14. And once we do that, we're going to realize how many carbon and hydrogens we've got left to play with. And if we go 20, take away 8, that's 12, take away 6, I'm left with 6 carbons, and then let's work out how many hydrogens we're left with. So we're going to go 42 hydrogens, take away 10 is 32, take away another 10 is 22, take away 4 is 18. So we are left with C6H18. Now, I reckon quite a few people might have written that as their answer, but you would be wrong because there are no alkanes with the formula C6H18, and you should know off by heart that alkanes have the formula CnH2n, call this the general formula, I should say, H2n plus 2. So that is the general formula of alkanes. So what this means is this cannot be our answer. So maybe if we try and divide it by 2, and so we make 2 lots of them, we'll get C3, what's 18 divided by 2 is 9. Does that fit that formula, C3H9? No, it doesn't, because that's plus 3. That's times 2 plus 3. Let's divide it by 3 and see if we can get one of these multiples to fit the formula. And I know there's only one line, so it has to be a multiple of an alkane. It's not like plus and plus. I can do 2 different numbers. There's going to be a multiple of one formula. So if I divide it by 3, I get C2H6. And boom, that's ethane. And that fits the formula, doesn't it? Because if I go C2 times 2 is 4, plus 2 is 6. Yes. And so I'm going to need 3 of these bad boys right here to make that up. And I reckon that was a little trickier than at first glance. And if I was doing my A-level exam and I'm under time pressure, I think I might have made the mistake of H18 and not check that out. So don't punch yourself in the face if you got it wrong. Completely, well, give a suitable catalyst for this reaction. So there's a whole bunch of catalysts that could be used for this. Now, on the mark scheme, they'll allow you to say neolite, and they'll allow you to say sort of alumina and alumina. Oh my gosh, what happened there? Alumina and alumina is basically Al2O3. It's aluminium oxide. I'm pretty surprised they don't they haven't got silica on there, but silica is another catalyst that you can use in cracking, but maybe they don't want to let you have that. So there we go. Right, let's zing down to do the rest of this question. 3.2. Figure 2 shows the C13 NMR spectrum for the aromatic hydrocarbon C8H10. Okay, lovely. How many peaks, peeps? Can you count the number of peaks? 1, 2, 3, 4, 5. We're probably going to need that. All right. Oh, yes, we are. Which of these structures is C8H10? Tick one box. Is it A? Is it B? Is it C? Is it D? Now, just to show you, how would you identify that? It's going to be the one with 5 peaks, because here, the spectrum, there are 5 peaks, and those 5 peaks, all right, are equal to the number of carbon environments. So what we're looking for here is to find which of these A, B, C, and D has 5 unique carbon environments. Why don't you grab your pencil? You might want to draw these out on a bit of paper. This is really good practice because it's not straightforward. And people make a lot of mistakes on this, including myself. So grab your pen, draw these out, and then I'll go through it. All right, guys, I'm going to go through the answers. So if you wanted to pause, you better do it now. I'm going through them. Right, let's start with A. How many peaks does A have? What you have to imagine is at the end of a line on these skeletal formulas is a carbon environment. So we've got a methyl group. So that is going to be region 1. And it's going to be identical. Look, that's perfectly symmetrical to that. So this is going to be identical. Both of them have the same groups on their left and right as each other. So that is region 1. There is another carbon right here, and people forget about that carbon. I know I do sometimes. And that is region 2, and they're identical to each other. And then we have region 3. What is this? Is this 3 or is this 4? But this is definitely not 5. So this is defo. Um, yeah, this is only 3 regions because these guys are all identical to each other. These two are identical to those two, and that is identical to that in terms of what is on its left and right and going all around. They've got the same things. So there's only 3 regions here. So no, this has 3 regions. Right, let's look at B. Boom. Okay, yeah, I've had too much coffee. Right, that is a unique environment. Is it unique? Well, we'll soon find out, won't we? So, what do we want to do? I want to go. It's going to be identical to this environment. Now, this might catch you out. Why are these two environments identical? Well, this one has a carbon there and then a methyl group. And then you could look to this one side and go, well, it has a carbon and a methyl group. So all's fair in love and war. And then on the other side of this one, it has 1, 2, 3 carbons before that methyl group. And if we look on this one, it has 1, 2, 3 carbons before a methyl group. So their surroundings to the left and right going clockwise and anti-clockwise are basically the same as each other. So they're the same group. And that means that this carbon here is also going to be identical for both of these. So that's 2 unique environments so far. That's going to be number 3 for them. And that's going to be number 3 for them. Now, is this group the same as that? No, this group is a totally on its own groupy group. And that is going to be another unique group. And why is that different than everything else? There's no other carbon that has a carbon with a methyl coming off on its left and right. No one else has a carbon and then a methyl, carbon, then a methyl on its left and right. So that's unique. No one else, look at 4. Why is 4 unique and not the same as 3? No one else has a carbon, then a carbon with a methyl, a carbon, then a carbon with a methyl. No one else has that. So that's unique to that. So that is our correct answer because it has 5. Now, this is painful watching me do this. So you might want to flick over to 3.3, but I'm going to go through and explain how many regions are in the others just for your practice. So this is good practice for you. So how many regions do you get with these? You might want to pause the video and see if you can do these two and work out how many carbon regions are in each of these. So these two guys, whoopsie, these two guys are going to be identical, aren't they? They're going to be identical. They're going to be identical, identical. That is identical, identical, and these two are identical. So C, as far as I'm aware, 1, 1, 2, 2, 3, 3, 4, 4. I think I've done that right. That has 4 carbon regions, unique peaks. And D, oh my gosh, D is going to have 1 here for the methyl group there. Then this is going to be unique. In this, what's that? That's like a propyl. 1, 2, no, it's ethyl. What am I on about? Yeah, so that's like ethyl benzene. So those two are going to be different. That is going to be a third. This is probably going to have the most. What are this then? 4, 4, 5. Oh no, this one's got 6. Yeah, it's got the most. 5, 5, and then 6. So this has got 6 groups. So it went 3, 5, 4, 6. So our correct answer was this one with 5. Oh dear. Let's move on. 3.3. Cracking can also be done without a catalyst using a temperature of 1200 Kelvin and a pressure of 7000 kilopascals. State the type of product that is formed in a high percentage in this type of cracking. So you can pause the video, have a go. Right, I'm going to go through the answers. There's 2 types of cracking. We've got catalytic cracking, which is done with the zeolite or the alumina catalyst that we've just been talking about earlier. But then you've got one called thermolytic cracking, where you use dirty high temperatures like that, 1200 Kelvin, and a high pressure. And what that does is that means that there's enough energy to smash through all the bonds and make to actually form lots of double bonds. So this is going to form alkenes. Okie dokie. We're going to make alkenes. Just so happens, what you have to know off by heart is you make alkenes. I think when you make alkenes, you actually increase. Generally, if you make alkenes over alkanes when you do cracking, if you have a high amount of alkenes being produced, it means you're going to have more particles and you're going to get a greater entropy, I guess, because they always favor disorder, don't they? Anywho, you don't have to know any of that. You just have to know that alkenes are made in thermolytic cracking. Right, let's move on. Wow, I thought this question was easy, but it's actually had some tricky bits in it. Oh, 3.4. A sample of butane has a volume of 20 centimeter cubed at room temperature and pressure. The sample is burned completely in 1350 centimeters cubed of air. The final mixture is cooled to room temperature and pressure. Calculate the volume of gas in the final mixture. Assume that air contains 21% by volume of oxygen. 4 marks. They've given us the equation with the coefficients, which is always nice. And really, really, really key here. what they've told us is that we're at room temp and pressure. So rather than having to use moles, rather than having to use 24,000 centimeters and divide centimeters and work out into moles, you can do that if you really, that's your game, right? But we don't need to because at this point, the amount of centimeters is equivalent, correlates to these coefficients. So we're totally cool because it's at room temp and pressure. So what we want to do, what's the actual calculate the volume of gas in the final mixture? Ah, tricky. Assume that the total volume of gas. Now that means they essentially want us to calculate the volume of air and the volume of gas from the reaction mixture. Okay, 4 marks. Grab your calculator, grab a pen, grab paper, pause the video, have a go. This one's a tricky one. All right, this is quite a tricky one. So I'm going to go through it with you. So we've got a ratio of 1 to 6 to 4. I'll put to 5 in there, but we might not need that. And let's go through. So I've got 20 centimeters of butane. How much oxygen is needed? So I've got 20 centimeters of butane. How much oxygen do you think is needed? Well, we're going to times by 6.5. And if you do 20 times 6.5, we're going to need 130 centimeter cubed of oxygen is what's going to get used up. But how much oxygen do we have? So this is how much oxygen from air will be used up. Now, will there be any butane left? No, the butane will all disappear. So we don't worry about that 20. That's not part of our final mixture. And this 130 oxygen isn't either. But we need to know how much is left. There's 1,350 of air. And how much oxygen is there in the room, peeps? Well, you're going to times it by 21 divided by 100, same as doing 0.21, right? And that's because you're trying to work out what amount in centimeter cubed of oxygen we have available. So we know that 21% of all the air in this mixture is oxygen. So 21 times 1350, what do I get? I get 283.5 centimeter cubed of oxygen. Now, this is amount of oxygen in the air. Now, how much is left? So how much O2 left over in final mixture? What do we reckon, peeps? I reckon we got to do 283.5 minus 130 equals 153.5 centimeter cubed of O2 left. So we definitely know we've got 153.5 of oxygen left in our final mixture. But have we got any other gases that would be made? Don't include the water. And I reckon some people will have included water here. Water is not going to be a gas because it says it's cooled to room temperature and pressure. Check that. It's cooled to room temperature and pressure. So this is going to be a liquid. So don't count as this will be liquid. Oh my days. As this will be liquid and not gas. I know during combustion it will be a gas for a while, but then it's going to become a liquid. So don't count the water. Let's work out how much of this we're to make. Well, we know we've got 20 of that. So we're going to go 1 to 4. So because it's 1 to 4, we're going to go 20 times 4 equals 80 centimeter cubed of CO2 will be formed. So it's easier to work it out from the amount of butane made. We know butane's the limiting reactant. There's only 20 centimeters of it. So the max carbon dioxide we can make is 80 centimeters. So now I'm going to have to do 80 plus 153.5. What does that equal? What does that equal? 153.5 plus 80 equals 233.5 equals 233.5. And so I reckon some other people put that as their final answer. I reckon if you were marking hundreds of exams, other students will have put that as their final answer. And I think that's a fairly good answer. That will get them 3 out of 4 marks. But what they've forgotten here is the rest of the air. There's loads of unreacted air. In fact, what's not getting involved? We've got 79%, so 79 over 100 of nitrogen that didn't get involved but is still there. So 79 over 100 times 1350 tells us how much nitrogen is in the air. So we're going to do 79. Oh, let's just go naught. Come on, Tom, sort it out. Times 1350. And that equals 1066. So we got 1066.5 centimeter cubed of nitrogen gas. So we're going to whack those two together, add them together, and what we're going to find, add 233.5, and that equals 1300. Boom! Yeah, love it. All right, nice one, guys. Welcome to Let's Get to the Marks. This question is about the preparation of an ester. 4.1 ester F can be prepared from propan 2-ol and ethanoic acid. Give an equation for this reaction and name ester F. So you write equation here and you put the name down there. I'll probably name it first, I guess. 2 marks for this one. Why don't you pause the video, grab a pen, grab some paper, and have a go at this one. All right, I'm going to go through the explanation. So first of all, I'm going to draw out the reactants. I've got propan 2-ol, so main chain has 3 carbons. Second carbon will find the hydroxy group. And then we've got ethanoic acid, so total of 2 carbons. We've got the methyl group at the end. We've got the carboxylic acid group there. Now they're going to come together. And what's going to happen when they come together? Do you remember the name of the reaction? It's a condensation reaction. So we're going to lose a water molecule. So essentially the OH from the hydroxy is coming off and the H from the carboxylic acid is coming off like that. And then you just join them together at that point and you're going to get a water molecule as well formed because of the 2 H's and the O. So what's the name going to be? Well, you could call this propyl and then ethanoate. The carboxylic acid always gives the carboxylate ion. So like ethanoate, propanoate, butanoate. So it'll be always ethanoate. But there's some variations on how we name the side parts. So, for example, there's an ethyl and a methyl, but the ethyl is connected to the main chain. So we call it ethyl ethanoate, but then we want to acknowledge that there's a methyl side group that I've circled in brown there. So we might call it ethyl ethanoate, but then stick the methyl at the front. So call it methyl ethyl ethanoate. Of course, we don't need to number it because if the methyl group was on the other end, it would just be propyl ethanoate. So yeah, it'd just be methyl ethyl ethanoate, or you could call it 2-propyl ethanoate if you like. Now we just need to bust out the equation. So you want to write the structural formula here, and you want to bust out the structural formula of the reactant. So the structural formula of propan 2-ol and the structural formula of ethanoic acid, and then the structural formula of our methyl ethyl ethanoate or 2-propyl ethanoate, whatever you like to call it. So I'm just writing in the ethanoic acid, CH3COOH here. Then we're going to do a little arrow. And we're going to form a water molecule because it's a condensation reaction. But I also want to get rid. Oh, I need to write the full structural. So I'm going to start with the ethanoate part. So CH3COO. And then that is attached to the propyl part. So we're just going to put CH for where it's attached, then CH3 brackets 2. And there we go. And plus H2O. Boom! Okay, moving on to 4.2. So if we just zing down, it says this method is used to prepare a sample of ester F. Mix 10 centimeter cubed of propan 2-ol with 10 centimeter cubed of ethanoic acid, add 5 drops of concentrated sulfuric acid and reflux this reaction mixture for 20 minutes. Step 2, transfer the cooled reaction mixture to a separating funnel and add 20 centimeter cubed of aqueous sodium carbonate and shake the mixture. Step 3, transfer the organic layer to a beaker, add 5 grams of anhydrous magnesium sulfate, decant off the organic liquid. Step 4, collect the ester using simple distillation. 4.2, describe how step 1 should be done. In your description, you should include details of suitable equipment used to add each reagent to the reflux apparatus. Draw a labeled diagram of the apparatus used for refluxing the reaction mixture and explain any safety precautions needed other than eye protection. Pause the video, have a go. Right, I'm going to go through the answers for you. It's a 6 marker, so I'm now going to go through everything you need to get those 6 marks. First of all, you could say use a measuring cylinder to measure out 10 centimeter cubed of ethanoic acid and 10 centimeter cubed of propan 2-ol and mix together in a pear-shaped flask. Of course, you could use a volumetric pipette. Should have 1p. I don't know why I put 2p's. And then use a dropping pipette to add 5 drops of concentrated sulfuric acid. You need to highlight that you're not using a volumetric pipette for the sulfuric acid. And that's going to score you 2 marks for just explaining how you've done that. Now, part of the 6 marks, I'd say another stage, which probably will equal up to get you into the 3 to 4 marks area, is if you do a decent diagram of reflux apparatus, because you're going to reflux this. So you want a pear-shaped flask or round bottom flask. I'm going to go with a pear-shaped flask, although my pear is a little bit. And then what we're going to do, we're going to draw our Liebig condenser in. Don't forget you're going to need an inlet for water to come in and an inlet for water to come out. Oh my days, what does the top of that look like? There we go. I did get a D in GCSE art, which is equivalent to like a level 3. Okay, now you've got to make sure that your condenser is open at the top and open where it attaches to the pear-shaped flask. You're then going to have a heat source. Personally, I wouldn't use a Bunsen burner like I've drawn there, but we'll talk about that in a little bit. So when we get to the safety. So hopefully you can think about what you should use instead of a Bunsen burner. Now that is your reflux apparatus. Now you just need to label it. So you want it to be an open system. So where the Liebig condenser meets the neck of the pear-shaped flask, they should be open, but it should go inside it. Then you've got anti-bumping granules there that can come under safety as well. Cold water should always go in at the bottom and push up against gravity, and the warm water comes out. That's to ensure that the Liebig condenser completely fills and you get the most efficient energy transfer. And it should be not closed at the top, and then you're going to get all of the marks for that diagram. Make sure all of these regions, all these ones I've circled in pink, are your vital regions when doing your reflux system. Okay, so we'll have probably picked up 4 marks now because we've done the diagram as well. Now to just finish it off with the safety fume cupboard. Why? Well, you're dealing with concentrated sulfuric acid. You can imagine the vaporous fumes off of that. The going to be corrosive. I don't even know if vaporous is a word, but the vapors are corrosive. That's why I'm laughing. You might want gloves as well. No, I don't know if corrosive's 1 R, is it, or is it 2 R's? I never know. I've spelt it both ways just in case. Use a water bath. Don't use a Bunsen burner. I originally drew a Bunsen burner, but of course, those fumes, those organic vapors, the sweet ester that you're making, esters are very volatile. Maybe they're going to catch on fire and burn your face off. So use a water bath for this so you get a gentle heat. Also, make sure you leave the top of the Liebig condenser open because we don't want pressure to build up and it to explode. Also, use anti-bumping granules. This is going to help um, break up large bubbles that may form in the reaction mixture. Okay, let's move on. We're on 4.3, folks. Step 2, the reaction mixture from step 1 is shaken with aqueous sodium carbonate. State the purpose of the sodium carbonate. So just the precaution that should be taken while the mixture is shaken. Why don't you pause the video and have a go? Right. Well, we got sulfuric acid reacting with the sodium carbonate, but also really it's not so much the sulfuric acid, that's the catalyst. It's more likely going to be any excess ethanoic acid because we were using, what was it, propan 2-O1 acid. So it's going to get rid of any excess carboxylic acid, going to neutralize it. And why should we leave the top off the funnel? Well, carbonates, what do they produce with acids? They produce carbon dioxide. They make salt, carbon dioxide, and water. Carbon dioxide's a gas. If you had a lid on the top of the separating funnel, boom, it will explode. So separating funnel, don't get it confused with the Liebig condenser. 4.4, give the reason for the use of the anhydrous magnesium sulfate. That should be the clue. Anhydrous means without water, so it's a drying agent. It will quickly form a hydrated salt. It will absorb that water for us. Suggest how the purity of the ester can be confirmed. Purity, you should notice from GCSE as well as A level, can be confirmed by melting point or boiling point. In this case, we want to compare the boiling point of the ester that is created to known values in a data book. And remember, pure substances have exact boiling points. You've got a bit of a mixture, an impure substance if you have a range. Okay, we're on question 5. This question is about simple test tube reactions to identify organic liquids. Silver nitrate solution can be used to distinguish between propanoyl chloride and 1-chloropropane. Give the observations you'd expect when a few drops of silver nitrate solution are added to separate samples of propanoyl chloride and 1-chloropropane. It's worth 2 marks. Why don't you pause the video, see if you can do this one, and then I'll go through the answers. Not an easy one, actually, quite tricky. Okay, so let's have a little look. Silver nitrate solution, that's AgNO3, AQ, and we've got propanoyl chloride. Let me draw out propanoyl chloride. Prop means 3 carbons. Oil means it's an acyl chloride, so it's got the carboxylic acid carbonyl group, and then it's got the chloride instead of the OH. Now, my water from the aqueous solution is going to attack that carbon. Why? Because that oxygen has an electroinductive effect and removes electrons from the carbon, making it positive. So that water molecule is going to want to attack there. The chlorine's going to break off. The hydrogen's going to end up breaking off. And that means we're going to get hydrogen chloride form, which is what you get with acyl chlorides. You're going to get misty white fumes of hydrogen chloride forming. Okay, now what happens to the silver nitrate? Well, silver Ag plus ions are going to react with some of those chloride ions that are knocking about from the hydrogen chloride that might dissolve in the solution. And therefore, we're going to get silver chloride formed. And you might know from your halide ion test that silver chloride forms a white precipitate. Okay, so we've got the white precipitate, we've got the misty white fumes, possibly. Either of those, I think, will get you the mark for the propanoyl chloride. Now, what do you get with the observation with 1-chloropropane? Now, alkanes are notoriously less reactive than a lot of the other molecules or compounds or homologous series that we do in organic chemistry. So, why is that? It still contains a carbon-chlorine bond, exactly the same as in the acyl chloride, you have a carbon-chlorine bond. The difference is this one is stronger because it doesn't have that carbonyl oxygen attached to the carbon, which would withdraw electrons from the carbon, making it more susceptible to nucleophilic attack. So it's going to, if it does form any sort of AgCl, it's going to be a slow formation of the white precipitate. You can probably say, I'd have to check the mark scheme, but you'd probably say it doesn't change at all. I wouldn't witness a change in a test tube reaction, or it slowly forms the white precipitate with the key on the word slowly. Right, 5.2, 3 unlabeled bottles of either propan 1 or propanol or propanone. A sample of each liquid is warmed with a few drops of failings. Identify the liquid that reacts with the failings and give the expected observation. Suggest a further simple test tube reaction that can be used to distinguish between the remaining two liquids. Give the expected observation with the liquid that reacts. And that's worth 3 marks. Pause the video, have a go. I've given you a clue. All right, I'm going to go through the answers. So obviously propan 1-ol is an alcohol. It's actually a primary alcohol. Propanol is an aldehyde and propanone's a ketone. So with failings, which one will change the color of the failings? Failings is blue. It will form a red precipitate, brick red precipitate with an aldehyde. So it's a bit like the old Benedict's test, isn't it? And it will only do that with those primary alcohols as they get oxidized to aldehydes. Now, why won't it change with the ketone? The ketone's already oxidized, so cannot oxidize further. Um, so further test, react with potassium dichromate, K2Cr2O7, and it will turn from orange to green with the primary alcohol, but it will not react with the ketone as the ketone has already been oxidized and cannot be oxidized further. There are no more hydrogens attached to the carbon atom that has the carbonyl group, so it can't be oxidized further. And that'll get you all the 3 fat Badman marks, and that's the end of the question. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Okay, this is a tricky organic analysis NMR one. So let's go. Question 6: compounds V, W, X, and Y are isomers with the molecular formula C5H10O2. Isomers V and W are carboxylic acids with formulas that can be written as C4H9COOH. Give an equation for the reaction C4 H9COOH with sodium hydrogen carbonate. Pause the video, have a go. You know this one, easy peasy. You're just looking at a carbonate with an acid, right? Essentially. And what do you make if you do carbonate and acid? You know this from GCSE chemistry. You're going to make salt, carbon dioxide, and water. So the salt here, we've got like, I don't know, we don't even know what structure it has, but butanoate. So it's going to be like sodium butanoate, essentially. You don't need to put the minus and the plus. I'll probably get rid of that. Plus water, plus CO2. Yeah, let's get rid of that minus and plus. Normally on mark schemes, they accept that, but, you know, best not to. There we go. So let's go to 6.2. An isometric, isomer V. So one of the 2 carboxylic acids, because we're told they're V and W. So the first carboxylic acid V has an asymmetric carbon atom. Deduce the structure of V. So what we want to do here is pause the video, grab your pen, grab a scrap bit of paper, see if you can work out what structure V is. Now remember that chiral carbons are ones that, or asymmetric carbons, that's just another name for a chiral carbon. They have 4 different groups attached. So play around with the structure. We know the molecular formula is C4H9COOH. Play around until you can find a carbon that has 4 different groups attached. Get that practice in, make it active. All right. Let's go through the answers. There's no point in just watching me go through the answers. You need to play around yourself and get used to it. So here is our straightforward, whatever that is, pentanoic acid. Now you can see there, that can't be chiral. Why? I've put a star next to that carbon. It's got 2 hydrogens attached, right? So all I'm going to do is take a methyl group. So that's how I would start. I would start by drawing that out and then look what I've got to do. Take a methyl group and attach that to that carbon there. And now what you're going to see is I've got an ethyl group here. I'm just putting the hydrogens on. So now we've got this ethyl group. There we go. Oh God, I'm going to delete this. It's all a bit close and club. Right. There's nothing wrong with it, but it's just visually hard to see what I'm talking about. So what I've done is I've moved the first carbon down and stuck it coming off the carbon number 2, or the fifth carbon, sorry, and attached it to carbon number 2. Carbon 1 will always be the one with the carboxylic acid. It takes priority. So we've got an ethyl group, a methyl group, a hydrogen atom, and a carboxylic acid group. That is a chiral carbon, asymmetric, carbon atom, isomer V. Now we're going on to 6.3. Isomer W, which is the other carboxylic acid, has 4 peaks in its H1 NMR spectrum. So it has 4 peaks show up. Deduce the structure of isomer W. We know it's a carboxylic acid. Deduce the integration ratio for the 4 peaks in the H1 NMR spectrum of W. It's worth 2 marks. Grab your pen. I think this is particularly tricky. I'm going to go through the answer, so don't beat yourself up. But again, you're just trying to rearrange the structure. It can't have the same structure as the V, the one we just did. What was that? 2-methyl-butanoic acid. It can't have the same structure as 2-methyl-butanoic acid, but it's got to have the same molecular formula. So just rearrange it a little, because we still know it's a carboxylic acid, and try and work out the structure. Deduce the integration ratio for the 4 peaks. Let's go. Okay, so if we look at the previous question, we did isomer V. We know this is just an isomer of isomer V, so I can't put the methyl group there on the first. I could try butanoic acid. That's not going to work. I kind of, we need 4. What does it tell us here? Oh my gosh, it's got 4 different peaks. So I need 4 different hydrogen environments, 4 different hydrogen environments. One of those hydrogen environments, let's do it. And we've got to write down the integration ratio and the structure. So I'm going to try this structure. I've just moved the methyl group 1 over. And look, we've got 2 methyl groups there, same hydrogen environment. I've got, so that means I'm going to have an integration trace of 6 for that hydrogen environment, because they're both identical environments. Now I've got this, which is a unique environment, a CH, and that's going to go, it's got 1 hydrogen, so it's going to have an integration ratio of 1. The OH is going to have an integration ratio of 1, and then I have this CH2 group here, which is another hydrogen environment, and that has an integration ratio of 2. So I would get 4 peaks here. And there we go. It would be 6, 1, 1, 2. And there we go. 2 marks. Lovely. Right, 6.4. Isomer X has 3 singlets with an integration ratio of 136 in its H1 NMR spectrum. Deduce the structure of X. This no longer has to be a carboxylic acid, and it definitely won't be a carboxylic acid. So we need to get that molecular formula down. It won't be a carboxylic acid because it told us W and V were, but it has the same molecular formula, so C5H10O2. So I definitely need to write down the molecular formula, and I need to rearrange the structure so that it has 3 singlets, so 3 hydrogen environments that produce singlets, which with a ratio of 136 in the HNMR 1 spectrum. Explain why the peaks in the spectrum are singlets. Now, there's a whole bunch of ways. What can I do with these O's? We know it's not carboxylic acid, so I could have carbonyl group COO bonds. I could have OH bonds coming off. I could do some sort of ester link where you have like an oxygen atom in the middle. So let's have a little look. The integration value of 6 makes me think it's CH3 times 2. But then I know it mustn't have any hydrogens on the adjacent carbon, right? Because they're telling me that all the peaks produce a singlet, all the poops. So I know that here, this would have an integration ratio of 6, the CH3 and the CH3, but that carbon cannot have a hydrogen on it. So I don't know, I'm going to stick an oxygen coming off of it and a carbon coming off of it. I could, as long as I don't have another hydrogen coming off, that would produce a singlet, because a singlet tells you there's no hydrogen on the adjacent carbon. So let's just try and get all the I'm going to put there must be loads of compounds you could do with this. I'm going to get a carbonyl group there. Let's put a carbon there. I just need to make sure I've got all with the molecular formula. Okay. Yes. Let's see. I would get, you see, I've got this methyl group here. That is an integration ratio of 3. So this one on the right-hand side has an I for integration of 3. It's a singlet because the carbon next to it, I've stuck a carbonyl, I've stuck the COO bond, so there's no hydrogen on that. That's why it's a singlet. And then this hydrogen atom on the OH would produce a singlet as well, because the H has no atom next to it with a hydrogen attached. It's got an oxygen, actually, not even a carbon. So this formula, this structural formula or display formula, would give me 3 peaks in a ratio of 1:3:6. So this is my viable answer for the marks. I have to say, it's a tricky question. Don't slap yourself in the face if you found this really hard to do. This NMR takes practice, 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 practice for you to get excellent at it. It's a skill-based topic, not a memory recall topic. 6.5, Table 2 shows the information about the peaks in the H1 NMR spectrum of isomer Y, chemical shift 3.65 and 1.19, integration ratio 2 and 3. We got splitting pattern, singlet, singlet. Draw the parts of structure Y that can be deduced from each of these peaks, deduce the structure of Y, and then state how many peaks in the C13 NMR spectrum of Y, and it's 6 marks. Boom! Pause the video, have a go. Right, I'm going to go through the answer here. So you've got to bust out your data sheet and you've got to look up 365, and you're going to get your first marks on the board by just looking up, look, 3.1 to 3.9 chemical shift. It has to be ROCH. Now, it can't have the chlorine or bromine attached, which is 3.1 to 4.2, because there's no bromine or chlorine in our molecular formula. So always check what's in your molecular formula. Now let's look at 1.19. That goes 1.19. Oh, check it here, 0.7 to 1.2. It's going to be a CH3 group. So we now know, and you're going to get 2 marks out of 6 for this, for saying the 1.19 is a CH3 group and 3.65 is the RO group. So let's get this down. The molecular formula, remember, is C5H10O2. I'm going to go through the answer. So the 3.65 told us that it had to be the RO group, which we could see from our chemical shift data. Now, the fact that it had an integration ratio of 2, and that as 1H, tells me that there's going to be 2 of these O groups. More than likely, I'm going to end up with 2 of them because the integration ratio was 2. Now, why does that mean I'm going to end up with 2 of these bad boys? We'll come on to that. The total integration ratio is 2 and 3, which is 5, and that is half the amount of hydrogens. So actually, each one of them has probably got 2 hydrogens attached, and so you're going to attach those together because it's one environment with an integration trace of 2. You might say, how do I know that 2 is 4 hydrogens? Well, the total integration ratio is 5, 2 plus 3, and there's 10 hydrogens. I'll explain a bit more about that in a second. So I'm going to do 2 of those RO groups where the R bit is CH2, and I'm going to join them together to make one environment, one peak, like that. Now, 1.19, we're going to go with it CH3, isn't it? We worked out that the chemical shift was CH3. You'll get 1 mark for that, for identifying 1.19 as CH3. Now what I need to do again is look at this integration ratio. Remember, the integration ratio is 3 and 2, which is 5. The total integration ratio is 5, but we have 10 hydrogens with an integration ratio of 5. So each integration ratio point unit, there's 5 units there, each unit is worth 2 hydrogens. So 10 divided by 5 is 2. So as the integration ratio is 3, this means I've got 3 times 2. I must have 6 hydrogens in this hydrogen environment. Okay, so there's 6 hydrogens in this hydrogen environment. If the chemical shift is CH3, I've got 2 CH3 groups. So I've essentially worked out all my stuff. I've got 2 CH2s because of the integration ratio of 2. And then I've got 2 CH3 groups because that has 6 hydrogens, and we worked out 2 hydrogens per integration ratio point because there's a total of 5. So these 2 CH3 groups must be connected because they're part of the same hydrogen environment. So I need to connect all of this stuff up. So what I'm going to do here, I know I need a 5th carbon because I've got 5 carbons. So I've got 2 CH3s, 2 CH2Os, and I'm going to have to stick a random carbon in the middle here. Now, there might be more than one structure, but this is a viable structure. So there might be more than one structure you'd have to check the mark screen. I'll put the link in the description to the exam paper where you can scroll through to question 6 and check the mark scheme on this one. But I'm going to connect my two CH3 groups like this. Now, why do they give us a singlet? Think about it. They have an integration ratio of 3 because I worked out that each integration ratio point is worth 2 hydrogens. So 3 times 2, 6 hydrogens. They are connected to a carbon that has no hydrogen on it. So that is why it gives off a singlet. And the reason why the other hydrogen environment gives off a singlet, the ROCH or the CH2O, is because they're connected to the O's, which obviously do not have hydrogens attached. So we've got 2 separate hydrogen environments, one with 6 hydrogens, integration ratio of 3. And then we have this one up the top here. Obviously, they're singlets because they're connected there. But then this one up the top here has 2 CH2 groups. And that's why they have an integration ratio, an I of 2. Each I integration ratio point is worth 2 hydrogens here. We can tell that by looking at the molecular formula and working that out. Remember, the integration ratio is the ratio of the number of hydrogens. So the ratio is 2 to 3, because if we just did it as 6 to 4, then you can simplify that down by dividing both by 2 to go 3 to 2. So it's basically a bit like empirical formula there. And there we go. That is my final molecular structure. And that is going to get me 5 of the marks. So you're going to get 1 for working out the CH3 group is 1.19. 1 for working out the ROCH group is 3.65. 1 more mark for working out the 2 CH3 groups are connected in the same environment. To a carbon with no hydrogen. There we go. That's 2. 1 for working out the 2 CH2O groups are connected, right? And we know they must all be connected because we've only got 2 singlets in the splitting pattern. Oh, I forgot the 6th mark. How many peaks are there? Let me put the formula back up. There we go. Bush. Right. How many peaks in the CNMR? So all you've got to do, how many different carbon environments, not hydrogen, how many different carbon environments are there? So we've talked about the fact that there's only 2 different hydrogen environments, hence the 2 peaks. But how many peaks would you get on a carbon 13? Well, you get those are 1, that one in the middle is unique, and then those 2 are unique. So there's 3 different, so it'd be slightly different than the HNMR. You'd get 3 different CNMR 13 peaks, and that give you the 6th mark. Don't forget to subscribe, and let's get to the marks for all your help with A-level chemistry. All right. So question 7, this one's an amount of substance question. So why don't you have a read through with me? Compound L, Mr is 88, contains carbon, hydrogen, and oxygen only. 6.56 times 10 to the minus 4 moles of a sample of L burns completely in air to form 2.62 times 10 to the minus 3 moles of water and 2.62 times 10 to the 3 moles of carbon dioxide. Now they're equal, so the same amount of water and carbon dioxide. Deduce the formula of L and show your working. Why don't you press pause on the video, grab your pen, grab your calculator, a piece of scrap paper that you can chuck away after. Make your learning, your revision active, have a go at it, and then unpause, and I'm about to go through the explanation. Okay, so we know that compound L contains C, H, and O. I'm going to write that in black because the pink's a bit weird showing up sometimes. CHO, carbon, hydrogen, and oxygen. We don't know how much carbon, hydrogen, and oxygen. Obviously, that's what we've got to work out. We do know that it forms H2O, and it also, we get 2.62 times 10 to the minus 3, the exact same amount of moles of carbon dioxide. Now so we know that it burns in air, and we know that organic compounds made of carbon, hydrogen, and oxygen, they're going to react with oxygen in the air in a combustion equation to make carbon dioxide and water. So we can essentially write the equation out. And what we're doing here, we know that carbon dioxide and water are 1 to 1, and we know the moles of them. So let's find out how many moles we have of compound L, or what's the ratio? The carbon dioxide and water are 1 to 1 to each other, but what's their ratio to compound L? Well, we can do that by dividing the larger moles, which is 2.62 times 10 to the minus 3, by 6.56 times 10 to the minus 4, the smaller amount of moles of L. And this is going to indicate to us how many carbon atoms and hydrogen atoms are in L. And we should be able to work it out from this. So the answer is 3.99, which is, we can round that to 4. So essentially what that means is for every mole of carbon dioxide, every 4 moles of carbon dioxide, you're going to have 1 mole of L, because the ratio is 1 to 4, of 4 times the amount of carbon dioxide to 1 times the amount of L. We know that water and carbon dioxide are equal, so they're both 4. If we have 4 moles of CO2, we have 1 mole of L. So we've got 4 times the moles of CO2 than L. And what does that mean? That means that 1 mole of L must contain 4 carbons, right? Because if I have 4 CO2s, there must be 4 carbons in L to make up that. And there are 8, 4 times H2, 8 hydrogens. So the formula must be C4H8. Now we know the overall MR is 88. So let's work out how much of that MR is left for oxygen. So we're going to go 88 minus 4 times 12, which is 48, minus 8 for the 8 hydrogens, and that is totaling 8 plus 48, 56. So minus 56 from 88, we're going to get 32. Now, 32 is the MR left over that we have left for the oxygens. How many oxygen atoms make up 32? Well, there's 16 each, so it means our formula is C4H8O2. We've got 2 oxygens there. Now we know we need to balance the amount of moles of oxygen they combusted in. How many oxygen atoms are on the right-hand side in total? Well, if I had 4 carbon dioxides, that's 4 times O2, that is 8 O's. And if I have 4 times O in the water, that is 4. So add them together, 12. So I'm going to need to put a 5 here, which will be 5 times 2 to make 10, plus the 2 in formula L. And bish, bash, bosh, boom! We've scored all the marks. So you're going to get like 3 marks for working and then 1 mark for the formula there of L. So lovely jubbly. We did the balanced equation as well, but we didn't necessarily need to do that. But I thought, well, let's bust that out just to show you. All right. This question is about organic synthesis. So let's get into it. Don't forget, pause the video at the start of each question, have a go, then unpause, and I'll go through the explanation. So what we have here is some sort of alkene. What does that look like? Butene or butene or just butene? And then it's turned into oh gosh, what's that? 2-bromobutane. And then J, which we don't know what it is. After step 3, that looks like a ketone, carbonyl group CO. Let's have a go at this question. Name the mechanism in step 1. State the reagents used for step 1. And then for 8.2, identify compound J. State the reagents and conditions needed for step 2. Like I said, pause the video, get your pen out, see if you can have a go at these, and then unpause and check your answers off. Make your revisions active. So have a go first. If you don't have a pen and paper, just do it in your head. All right, let's go through. Okay, let's work out this first one. What kind of mechanism is this? Well, if we look, we can see that hydrogen and bromine have been added on after step 1. So the electron-rich bond is going to be attacked there. And if you have a look, you can see that a bromine atom and a hydrogen atom have been added on. So this is going to be electrophilic addition because we're adding atoms on. And if you don't understand that, you can check the hydrogens. You've got 3, 2, 6, 7. You've got 8 hydrogens on the left of step 1, and you've got 9 on the right. So it's addition. You've been adding to it, and you've added a bromine atom, and the double bonds disappeared. So it's electrophilic addition, and the reagent is hydrogen bromide. And just to confirm that for you, let's underline where the hydrogen and the bromine have been added on. Okay, let's zing on to 8.2. So identify compound J, state the reagents and conditions needed for step 2. So what we want to do is think what a halo alkane can be turned into that can then become a ketone. Look, the haloalkane has become compound J. We can see that compound J goes on to become butan-2-one. What do you make ketones from? You make them from secondary alcohols. What's the name of the secondary alcohol that would make butan-2-one? It's going to be butan-2-ol. Remember, we oxidize them. What is it? Potassium dichromate. We oxidize those bad boys with, don't we? And that will, in step 3, we would state the reagents and conditions needed for step 2. Well, for step 2, you are just going to break that down by adding an OH. So where are we going to get these hydroxide ions to turn that into an alcohol? We're going to get them from sodium hydroxide aqueous. But if you wanted to know again, then how do you turn butan-2-ol to butan-2-O? And they haven't asked that. But if you wanted to know how to go to butan-2-O, and that would be the old potassium dichromate, wouldn't it? Oxidizing agent. But they haven't asked that, so no need for me to waffle on about that. The conditions would be aqueous, so that your hydroxide ions can separate and attack. Right, 8.3, state the reagents used for step 4 and outline the mechanism of step 4. This is a 5-marker. You might want to pause, grab out your pen, bust out your paper, have a go. What I'm going to do is talk you through this. So remember, this was butan-2-one, which is over here, butan-2-one. Let's whip that out, no diddy, and just draw that here. So we've got the carbonyl group there. We've got the all the carbons and hydrogens. I'll add them on later. And that's butan-2-one. Now, we need to draw a reaction mechanism to show how, oh my days, we can see we've added a carbon there. Look, there's 1, 2, 3, 4, what is that? 5 carbons. So it's gone from 4 carbons to 5. We've extended the chain. That means we've been adding that nitrile. So yeah, like that. And the nitrile group has a lone pair with a negative charge. What's it going to attack? It's going to attack the carbon because the oxygen atom is withdrawing electrons in that double bond towards it, making the carbon delta positive. And because carbon is in group 4, it can only have 4 bonds. It can't have 5. So in order to form this bond with the nitrile, it's going to have to sacrifice one of its double bonds. So put those curly arrows on and then draw the intermediate. So the intermediate is going to be an oxygen with a lone pair and a negative charge. Oh, God, that doesn't look right. Hold on. Oh, I don't like the look of that. I mean, you'll get it for any negative charge and lone pair anywhere on it, but maybe that's a bit neater. Okay. I do need to stick the hydrogens on. Excuse me while I whack these on. Oh, I should have picked up 2 marks for these 2 little bits of the mechanism there, right? Now, what I want to do is make room for my, basically my nitrile there, the CN. I want to make room for that ion. So I'm going to attach it here. You can see I've done it in pink. I could really fold that methyl group further up, or I could put the nitrile on the top of that. It doesn't really matter where I put this nitrile. I mean, yeah, it's probably better to put it on the other side of the methyl group, really. That is not a very nice place for me to put it. Better to either have the oxygen above and the nitrile below, or the nitrile above and the oxygen below. Would be better, but I ain't going to rub this out because it's just going to take me forever. But that pink nitrile group I've attached, better to put it above the carbon, or and then the oxygen below, or have the nitrile below the carbon and the oxygen above. They're the 2 different formations for it. Right. Right. What do we need? So I've done the mechanism. That's going to get us 4 of the marks. Oh, reagents. Where do you get hydrogen ions from? So I just wrote a little note there. You're going to need your hydrogen ions from an acidic reagent. So you're going to need sulfuric acid possibly with your potassium cyanide. Hydrogen cyanide naturally has hydrogen ions in it, and so does not need to be acidified, but KCN is safer to use. Hydrogen cyanide is like seriously deadly. You need to do it in a fume cupboard. It's like not very good for you at all. So you're safer to use KCN acidified with sulfuric acid. Sulfuric acid will give you the source of the hydrogen ions. And what I'm trying to just point you out there is an exam technique. Whenever you're adding hydrogen ions, whenever you have hydrogen ions knocking about, you need a source of hydrogen ions. And sometimes in organic chemistry, that can be that one of the reagents, one of the things we're using is an acid. So just watch out for that. That's a little bit of exam technique that comes in that you can apply to lots of situations. Okay, so we're going to get 4 marks. We've got the 4 curly. Yep, we got 3 curly arrows. We've put the lone pairs. We've put the negative signs. The only thing I'm unhappy about, I'm just dragging this over here. The only thing I'm unhappy about is where I've put my CN on the second step of that mechanism. I've put my pink CN sticking out the side. Really, I want that above that methyl group that I've kind of diagonally crammed up to the right. So just make sure you make that change and have your CN vertically coming above the O, or you flip it around and have the O above and the CN below. That's what I would do, but you know what I mean? You still get the marks for that because these things can rotate. So there's rotation, so it doesn't really matter if I put it there. Right, explain why step 4 produces a racemic mixture. Why don't you pause the video, have a go? There's 3 bullet points for this that you need to know off by heart. So I would write down how do racemic mixtures form on your revision card. Then on the back have 3 bullet points that you've memorized. And essentially, the carbonyl bond, the CO bond, C double bond O, is a planar bond, very much like the alkene bond, the C double bond. It's a planar bond. You've got no rotation around that bond. What that means is that the nitrile ions can attack from above or below the bond. So they'll either form above or below, and the probability of them attacking from either side is 50-50. And when they do, there's no rotation. So they're locked in that position, and that's how we get enantiomers. So what we want to say is CO bond is planar. There's an equal chance of the nucleophile attacking from above or below, meaning that there's a 50-50 chance of either enantiomer forming. And when you have 50-50, we call that a racemic mixture or a race mix. And here we go. That's worth 3 fat marks. So make sure you know those bullet points. Planar bond, 50-50 chance of it attacking above and below, and equal chance of either enantiomer forming. So either mirror image has a 50% chance of forming. Welcome to Let's Get to the Marks, going through an A-level chemistry question on amines. Let's get on with a walkthrough. This question's about amines. 9.1. An incomplete equation for step 1 in the reaction between bromoethane and an amine is shown. Complete the equation. In step 2 of this reaction, the product of step 1 forms a secondary amine. Name the secondary amine formed. So these 2 little bits are worth 2 marks. Why don't you pause the video, grab a pen, grab a paper, try and have a go on some scrap paper, and then unpause and watch the walkthrough. Okay, look, check this out. There's a bromine atom on the bromoethane, and obviously the bromine atom has come off. It's become a bromide ion, and we can see here that this bit I've circled in green has replaced the bromine atom. So all I need to do is redraw that. With that bit there, all I need to do is redraw that and show the other reagent, which is going to be this, methylamine. So we're just going to draw methylamine out here. So just like that, easy peasy. You could count up the H's, count up the C's, N's, and BR, and make sure your conservation of mass, everything's the same. So that one was quite easy. Step 2 of this reaction, the product of step 1 forms a secondary amine. Name the secondary amine. So what happens? Let's look. This at the moment, if we look at the nitrogen atom on our product here, it's got a positive sign on it. It's not an amine. It's like an ammonium right there. So what we're going to do is this hydrogen is going to donate its pair of electrons from its bond to the nitrogen, and that hydrogen ion, that H plus ion, is going to go on and join the bromide ion and become HBr, sorry. What I need to do is just redraw that -1 hydrogen and name it. Now I can't be bothered to redraw it, so I'm just going to scribble it out. Now, how do we name this? Well, this is actually an N substituted amine. And that is when you find a nitrogen atom in the middle of the carbon chain of an organic molecule, then you know it's an N-substituted amine. Now, we've got the 2 side groups. We've got the methyl group and we've got the ethyl group either side of the N. Now, think about it. It was actually methylamine, but now we've kind of got ethylamine because there's 2 carbons with a nitrogen on the end, and then we've got a methyl group. So how do we name that? Well, we can call it N-methyl ethylamine. There's a whole bunch of different names for this. But I would prefer the N-methyl group on ethylamine. And just to show you that, this would be what I would call ethylamine because the longest chain. So I like to call that ethylamine. And then just explain that there's a methyl group attached to the N. So the CH3 at the N there near the bromide ion is attached to the N. So I'm just kind of saying N-methyl ethylamine. And that is the name that I'm giving it. But there's plenty of other options. You can check them out for the other IUPAC options here in the mark scheme. Check out the link. 9.2. Right. We have, that looks like 2-bromobutane, and it reacts with ammonia. Draw the skeletal formula of the major organic product formed when an excess of ammonia is used or an excess of 2-bromobutane is used. Product with excess ammonia, product with excess 2-bromobutane. Grab your pen, grab your paper, pause the video, have a go, and then we shall go through the explanation. Okay, here comes the answer. Essentially, I'm drawing the skeletal formula. What I want to do is, with the ammonia, we're going to get the NH2 group swapping for the Br. So the Br is going to be substituted for an NH2. I just need to make sure with skeletal I've got the right amount of carbons. That's butane, isn't it? 4 carbons. Now remove those Cs. That's the skeletal. And at each point of the skeletal is a carbon. And what I want to do here is just attach the NH2. So that is my product with excess ammonia. You're just going to get all of those bromines on the bromobutane is going to be swapped for an amine group. So you're going to have, yeah, butan 2 amine or whatever it's called. Right, what have we got going on here? We have product with excess a bromobutane. So what's going to happen, because there's a lone pair on that amine group that's attached, the NH2, it's able to join to another one of these bromobutanes, and the hydrogen is substituted. So you can work out how many more can join. So look, it would start off like that. There's our NH2 group attached. Now another bromobutane would attack here. And so we're going to draw another one on, and that will delete one of the hydrogens. One of the hydrogens has been swapped. The bond area has been exchanged. Now look, the next bromobutane will come and attach because the nitrogen still has a lone pair, and that hydrogen goes, and guess what, we've now got 3 bonds around the nitrogen. That still means there's a lone pair left over. And remember, nitrogen can form 4 bonds, but it does get a positive charge, becomes a nitronium ion. And here, and just like in ammonia with NH4 plus, you're going to end up with 4 side groups, 4 of those organic molecules coming off the side. So this is a nitronium ion. And guess what? If you can think of the name for that, I'm going to try and name it really poorly, but I will attempt to name this. Okay, so what would this be called? You can put me up in the chat because I'm not sure this is correct, but yeah, I think this would be 222 tetrabutyl ammonium bromide. Okay, because you've got these butylamines, whatever they are, attached on the sides. Anyway, hit me up in the comments. Let me know if that's wrong. Let me know what the correct name for this quaternary ammonium ion is. Okay, let's go. Right, 9.3. Figure 3 shows a 2-step synthesis to make amine G. We got step 1 seems to have made a nitrile and released a bromide ion. Okay, so we're probably coming from a haloalkane, right? And then in step 2, we've got our nitrile being attacked by hydrogen and forming amine G. So complete figure 3 by drawing the mechanism for step 1 and the displayed formula of amine G. It's worth 3 marks. You know what to do. Grab your pen, grab your paper, have a go at this one. Pause the video so you don't watch the explanation first, and then unpause and I'll go through more or less how to do it. Let's hope. All right, I'm going to go through the answer. So we've got a bromide ion there. That gives me a clue that it looks like the bromide ion has come off. So that gives me a clue that something's been substituted for the bromine. That's going to be that CN, that nitrile ion, is going to have been substituted. So I'm going to draw out my little thing here. No, did he? So I've got CH32. That means, and a CH. That means that these 2 methyl groups are coming off a carbon with another hydrogen coming off. So where am I going to put that hydrogen? Who knows? I could put it here on the side, or I could put it down below. It's kind of my choice. And then the bromine would have originally been connected to that as well. Oops, let's put the bromine here. I don't know if I should put the bromide ion there or down below. Doesn't really matter, I guess. It's kind of 2-bromopropane, isn't it? The bromine is attached to the second carbon in the chain. So I could have just done a straight chain of carbons, but I think I'll do it like this to give room to show where the nitrile attacks. So this is going to be nucleophilic substitution because it's got a lone pair with a negative charge. It's attracted to that delta positive carbon. Now in AQA, you don't need to use the delta symbol, but I like to still do that just to show where it's going to attack. And then, of course, bromine can't have, bromine's going to have to break off. That bromide ion is going to be released because carbon can only have 4 bonds. It can't have 5. And there we go. That is going to be the steps. And that's probably going to get you 2 marks for the mechanism right there. Now let's look at amine G and what's going on here. So the clue here is that the nitrile is being attacked by the 2 hydrogen molecules. So I need to add 4 hydrogens on. You see I've written them down there in pink. basically I need to add 4 hydrogens to this to make amine G. We can see there's no other product, so it's an addition reaction. So I'm drawing this out. This is what it looks like at the start. This is what this molecule up here, the end of the product of step 1 would be. And now we're adding 4 hydrogens to this. So where am I gonna? I'm gonna need to get rid of that triple bond, right? And then you just fill out the hydrogens. So 2 hydrogens coming off the C. That's 4 bonds around the nitrogen, and then nitrogen, and then the nitrogen likes to have um, 3 bonds there. What did I say? 4 bonds around the hydrogen. Well, anyway, I'm waffling here. Carbon atoms only like to have 4 bonds. They're in group 4. So 2 hydrogens attached there and 2 to the nitrogen, which generally likes to have 3 bonds, although it can form that nitronium ion when it gets the positive charge. And I don't know what I would name this. What would you name this? 2-methylpropylamine? Or is it 2-methylpropanamine? What would you call this? Why don't you put in the comments what you'd call this? It's not one of the marks, but there we go. All right, let's move down to 9.4. Figure 4. Figure 4 shows 2 amines, P and Q. Explain why P is a stronger base than Q. So why is it that amine P is a better base? What do bases do? Remember the definition of a base? So why is it a better base? Okay, press pause on the video and have a go at this one. Now I'm going to go through the explanation. Check out these groups. What do we call these? These are alkyl groups or R groups. They're actually methyl groups in this situation. And you can see Q only has 1 methyl group, whereas amine P has 2 methyl groups. So what we want to say, it has more methyl groups or alkyl groups. These alkyl groups, you can see I've drawn a little arrow going towards the nitrogen. They have a positive inductive effect where they release electrons. They kind of donate their electron cloud towards the nitrogen. This increases the electron cloud around the lone pair on the nitrogen and makes that lone pair more available, it's able to accept a proton. So the lone pair on the nitrogen is more available and the nitrogen is more able to accept a proton. So if you look at the electron cloud on the lone pair on the nitrogen with the 2 alkyl groups, it's going to be bigger, and it's going to be able to accept that hydrogen. That's it. Sharing's caring. Hit the like, punch up the bell, subscribe. So why don't you grab your paper, pen, and have a go. Figure 5 shows the enthalpy of hydrogenation, data for cyclohexene and benzene. It also shows the predicted data for the theoretical molecule cyclohexa-135-triene. Now, just to remind you of what hydrogenation is, it's when you take a double bond, you add hydrogen across it, and you make it a single carbon-carbon bond. When you add hydrogen to something. Okay, so let's have a little look. We've got predicted data for 3 molecules, cyclohexene, cyclohexa-135-triene. Now, cyclohexa-135-triene is a theoretical fictitious molecule, but we would imagine that when you compare it to cyclohexene down here, this would be cyclohexene with 1 single bond, minus 120. We'd imagine the enthalpy release, the energy released with cyclohexa-135-triene should be 3 times that and should be 360, right? That should be the combination because you're adding 3 hydrogens, so it should release 360. Whereas benzene, therefore, if benzene had the cyclohexene 135-triene structure, benzene should also be minus 360, but it's not. Benzene is minus 208, so you can see there's 152 kilojoule per mole difference between the cyclohexa-135-triene and the benzene. Now comes the question 10.1. Compare benzene and the theoretical molecule cyclohexa-135-triene in terms of their stability, their shape, and their carbon-carbon bond lengths. Okay, so you've got 3 factors there to cover. It's for 5 marks. So let's check it out. Let's whip it down here. Why don't you press pause, get your pen, paper, have a go. But I'm going to go through the answers. So benzene is more stable. So they asked us to compare stability. Well, benzene would be more stable. And we can see this because when it is hydrogenated, like that, it releases minus 208 kilojoule per mole compared to the cyclohexa-135-triene, which releases 360 kilojoules per mole. So it's obviously less stable, the cyclohexa-triene. And we can even put a number to that, which we call the enthalpy of stabilization or the enthalpy of delocalization. There's, in fact, it's 152 kilojoules per mole more stable than cyclohexatriene. So benzene is more stable than if benzene really had this theoretical structure. So benzene structure gives it extra stability because of the delocalized ring. So we just want to mention that benzene has a delocalized ring of electrons, which makes it more stable. And then that will cover the first 2 marks, which is talking about the stability. Now, here's the burger shape of benzene. You've got the planar carbon ring with the hydrogens, and then above and below the ring, like 2 buns on a burger, you have the delocalized electrons, those 6 electrons donated. Now, we normally just show this as a round circle in here, and obviously skeletal formula, we don't need to show the hydrogen. So there's benzene structure. But when we talk about the shape, benzene is a planar molecule, meaning the hydrogens and carbons are all in the same plane. And however, so is I can't say this one, hexa 135 triene. And we know that because cyclohexa 135 triene has got those double bonds. You don't get rotation around those double bonds. So this is also a planar molecule as well. Now, so when we comment on the shape is actually similar. So I would say you get 2 marks for the first bit, talking about stability, 1 mark for the shape, because there's only a little bit to talk about there. They're both a planar flat shape. Now the carbon lengths, hopefully we get another 2 marks here. The carbon length of benzene, the CC bond in benzene, is about 140 nanometers, depending on what textbook you look at. Whereas the carbon length of a single bond, a single carbon-carbon bond, is like 154, again, depending on what you look at. Some say 156, but 154 nanometers long. Whereas a double bond, which is shorter, stronger and shorter, is about 133 to 134, depending on what you look at. So what we would expect with cyclohexatriene is that it would have irregular bond lengths. It would go 154, 133, 154, 133. When we look at benzene, all of its bond lengths are equal. They're 140. So it has regular bond length. And that is going to get us all at a 5 marks. Nice. Right, let's move on to the rest of the question. Make sure you hit the like. Listen, you molybdendium fluorides. I've noticed that people watch the videos, not that many, but they watch my videos, but they definitely don't hit the like, most people. So either they hate watching, which might be their kink, or just hit the like. 2 steps in the synthesis of an aromatic amine is shown. So we've got 1,2-dimethylbenzene. State the reagents needed for step 1. Give an equation to show the formation of the reactive intermediate for these 2 reagents. So we look at the reactive intermediate. Do you know your nitration of benzene content? If you struggle with this question, you need to make revision cards on the nitration of benzene. So essentially, we want to know what 2 things are needed to form NO2 plus, because that is our electrophile. And in order to form the electrophile, we use concentrated nitric and sulfuric acid. And you need to mention concentrated, both are concentrated. So concentrated nitric, concentrated sulfuric acid. The sulfuric acid acts as a catalyst, obviously, in this equation. Now, cool. Now we need to do the equation. Now you can do this equation in 2 parts. I'm going to give you the overall equation because they just want 1 equation. So you can do this in 2 parts where you first form H2NO3, but we're not going to do that. So where first of all, the sulfuric acid acts as the acid and donates the hydrogen to the HNO3 to make H2NO3. But I'm just going to give you the overall equation. So it's H2SO4 plus HNO3. We want our reactive intermediate. This is the nitronium ion. I'm going to put the plus there, but I could put the plus anywhere really, above the N or above the O2. And then we've got this H3O plus. And then we have hydrogen sulfate ions. And I've made a mistake. That doesn't balance. Hold on. Let me zing. Oh, what have I done? You can probably spot this before my brain does. What have I done here, folks? This doesn't balance. I've got a 2 there, 2 there. Oh, I've done a mistake. Where is it? Where is it? All up, all up, all up. Oh, I've written H2SO4. What an idiot with a minus. Yeah, you can't. Obviously, it loses a hydrogen ion, and that's why it's HSO4. It's hydrogen sulfate. I should have put that, not sulfuric acid. Yeah. Never mind, peoples. That was a big mistake. Let's move on. Outline a mechanism for step 1. Okay, let's get on with the mechanism. So what's the mechanism for step 1? Again, what I recommend is you bust out a revision card if you don't know the answer to this, because this is the nitration of benzene and it is the most common mechanism when you're dealing with benzene. So it is so common and it's repeated. So we're going to put our 2 methyl groups in the exact same place. We're not attacking those methyl groups, okay? So we're going to get this nitrate or nitronium ion, which is going to have a little positive charge on it. Don't know why I put a plus there. I'm going all over the place here, going a bit woo in the head. And then, oh my gosh, our intermediate, remember, we break the delocalized ring and you're going to draw a horseshoe. What's very important is that your horseshoe does not go past this dotted imaginary line that you do between carbons, like the two bottom carbons there. So it's very important that it doesn't go below there. And then you're going to add your hydrogen and your NO2 on. And the hydrogen is going to donate its pair of electrons to repair the delocalized ring. And I need to put that positive sign in the right place. And I should have had a 3 on my CH2 over there. What a bozo. That's supposed to be a methyl group. What a wally. Right. Okay, zinging down to 10.4 and 10.5. Remember to grab your pen and paper and have a go at these. State the reagents needed for step 2. State a possible use for the amine formed in step 2. Let's zing back up. Now, just out of interest, you might want to know, how would you name the the reactant there, that molecule there? That is 1 nitro. Oh my gosh, what's that? 4 dimethyl benzene, and that becomes a benzene with an amine on it. So it's going to be 1 amino 4 dimethyl benzene. Jeez, that was long, wasn't it? So anyway, you can use tin with hydrochloric acid as a reagent to add hydrogen, or you can use nickel or a platinum catalyst, so PT or Ni, and you use that with hydrogen. And that is the way to add hydrogen and turn your nitro group, your NO2 group, into NH2, into an amine group. And now it says state a possible use for the amine formed in step 2. Well, the amine formed in step 2 can be used as a cationic surfactant. Cationic surfactants, cations are positively charged ions. So their positive charge allows them to basically cancel out negative charge. Now, due to friction in your tumble dryer, if you're drying clothes, your clothes often get negatively charged. And hair, when you're like putting tops on and off or combing your hair gets negatively charged due to friction. And these cationic surfactants, they can cancel out that negative charge and make your hair feel smoother. So they're in conditioner, and they're also in fabric softener in your tumble dryer. Also, cationic surfactants can disrupt the cell membrane of bacteria and basically kill the bacteria as well. All right, guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Okay, welcome to the Let's. I can't speak, people. Welcome to Let's Get to the Marks. Well, I'm going through some combustion, A-level chemistry combustion question. This from the 2024 AQA A2 chemistry paper, all right, paper 2, organic paper. And this question's about the enthalpy of combustion. So question 11, 11.1, limonene is found in the skin of citrus fruits. Figure 6 shows a diagram of the apparatus used in an experiment to determine a value for the enthalpy of combustion of limonene. Limonene. Okay, however you say that. When 1.31 grams of limonene are burned, the temperature of 60 grams of water in the copper calorimeter increases by 52.1 degrees Celsius. The specific heat capacity of water is 4.18 joule kg to the minus 1. Calculate a value for the enthalpy of combustion in kilojoule per moles of limonene with a formula C10H16. This is worth a fat 4 marks. You're going to need your calculator, your basic mole calculations you've learned off by heart in your head, and formulas, and you'll need the specific heat capacity formula. So smash all that down, get your calculator, pen, paper, pause the video, have a go. Right, I'm going to go through the answer. So hopefully you had a go at this one, and I'm going to go through and you can check off your working out. So what I want to do, first of all, the way I tackle these questions is the way you should tackle these questions, is not by drawing random pink squiggles, unless you're into that, is to identify, when you've got a calculation, identify what your data is. So 1.31 grams, that's mass. And then over here, I've got when the temperature of water is 60 grams. Now, this is the mass of H2O. So I'm going to put a reminder with specific heat capacity. That's important. Copper calorimeter increases by 52.1. So that's not the temperature starting or final. That is the change in temperature. Little triangle with the T means change in temp. Okay, we've got the specific heat capacity of 4.18. And that's the grams one. It'd be 4,100, 4,000. Yeah, you know what I'm saying, right? I can't even speak properly if it was in kilojoules, but it's not. So that's our specific heat capacity. So look, I've got all my data kind of labeled up. I kind of know what I'm doing. Now I know I'm going to need the Q. Hopefully you do too. Q is energy in joules. and that equals mass. We're using grams here. I know sometimes you can use kilograms, and that is specific heat capacity times delta T. And delta T Kelvin degrees doesn't really matter. I mean, it is per Kelvin, but it doesn't really matter whether it's in degrees because one rise in a rise in 1 degree is equal to a rise in 1 Kelvin. Okay, the starting points are different. That's all. So we can put that as K if we like. Whatever. That's the specific heat capacity. So let's calculate an enthalpy of combustion. Now, remember, the enthalpy of combustion includes moles. So we are going to have to work out our moles, and we've got the MR. Anytime they give you a formula, you can label it with MR because that means you can calculate the MR, and that's a little N for moles. So what I want to do here, first of all, I'm going to solve this to find Q, the total amount of energy, and that's quite easy. This M is not the mass of fuel that's burnt down here. It's the mass of water that's being heated. The water is connected to the temperature increase, not the mass of fuel. So what we're going to do, we're going to go 60 Gs, 60 bad boy grams. We're going to times that by 4.18, and we're going to times that by the temperature rise, and that is 52.1. And smash that in your calculator. And this is what you're going to get: 60 times 4.18 times 52.1. We are going to get 13,066. So we're going to get 13,066. And I got a 0.68 there, 0.68, and that is joules. Now, that is Q. So we should pick up 1, possibly 2 marks for that out of the 4. The next step is we need to convert that into kilojoules because look, our answer needs to be in kilojoules and we're currently in joules. So let's go ahead and get another mark by dividing by 1,000, and that is going to zing me down into kilojoules. So let's divide that by 1,000, keep it all in the calc. I've now got 13 0.0666, oh my gosh, 8, and that is kilojoules. Now I want to find out per mole. This -1 means divided by moles. So I need to divide this by N. What's N? Well, you know your calculations, hopefully off by heart. Mass over MR times N. We need to find out how many moles of fuel we used. So we used 1.31 grams. So let's do 1.31 G divided by the MR of limonene. What have we got there? We got 10 times 12, that is 120, and then plus 16, so that's 136. So let's smash that into the calcs. 1.31 divided by 136 equals, I hope I've done this right, is that 120 plus 16 for the hydrogen, 136. Yeah, 1.31 divided by 136 equals 000963, whatever. Yeah, so I'm not going to write this all out because it's just going to take me forever. By this time, you'll have grown a beard. 0.00963, 235, whatever it is. Keep that in your calculator. That is your moles of limonene. So now we need to divide that by that. So divide that by that, and that is going to equal 13.06. So 13.06668 divided by ounce equals 1,356.454, and that is kilojoules per mole. Now, they're going to like 3 sig figs, so if they don't tell you, then do it to 3 sig fig. So what we're going to do, round this to 3 significant figures, that is greater than 4, 5. So we're going to take that up to 1360, and I'm going to give my final answer as 1360 kJ mole -1. Boom! And that's going to get you 4 marks. So I'm imagining that's the mark. You got 1 mark for converting there, 1 mark for working out the moles, 1 mark for dividing by the moles, and then giving the roundy. All right, let's go. Let's move on. We ain't got all day. We ain't got all night. Hi, this question looks long, a 5 marker. 11.2 table 3 shows the values obtained by different methods for the enthalpy of combustion of a different liquid hydrocarbon. Right, so we're going to answer this one again. You're going to need a pen and paper. So it's a liquid hydrocarbon. Why are they telling us that? Okay, method. The standard enthalpy of combustion at 298 K, so standard conditions, is -4194. Now, if you do this from calorimetry, you get a way smaller enthalpy of combustion, -1,100. So we're going to have to think of the reasons why is this lower. That's why is this lower than the real value? And then we have value is calculated just using mean bond enthalpies from the old data book. And this is also a little bit lower. So this is also lower than expected. So this is lower than expected too. It's nowhere near as bad as the colorimetry one, but suggest reasons for the differences between the values obtained by each of the methods 2 and 3, and the value obtained by method 1 in table 3. So basically, we need to say, why is the enthalpy from the calorimetry experiment much lower than this one? And why is the mean bond enthalpy lower than this one? So why are both of these not accurate? We're going to get into it. Why don't you pause the video, have a go? Okay, I'm going to go through the answer. So here we go. Right, when you're doing combustion, so just think about your little combustion. You got your, oh, I don't know why I'm on pink, but I'm going to stick with it. You got your flame, you're heating your water, right? You got your water in there, blah, 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 blah. You got your thermometer and you got your fuel in here. Of course, what can happen is some of the fuel can evaporate, and therefore you don't get an accurate answer. So we want to say method 2 is lower than uh, method 1. Oh my good gosh. We want to say why. Jeez Louise, can I make that bigger? Oh, no, did he? Right, method 2 is lower than method 1 as some of the fuel may have evaporated and not been burnt. So why does that make it lower? Well, it means that you assume you've used 1 mole of fuel when actually you've only used zero point 0.5 moles of fuel. Half of your fuel evaporated without actually heating the water. Now, that is one of the reasons, but there's other reasons here. There's 3 for colorimetry. Another one is, check this here, heat loss. Heat can escape unless you've got sort of insulation all the way around and insulation heat shields down here. You've got heat escaping there and there. You've got heat going out of there. Not all of it is going into that thermometer. So we want to say also there are heat losses, which reduce the enthalpy of combustion. So that via method 2. So that means we've got heat loss. And another one that we could have is incomplete combustion. Let's say not enough oxygen is getting into the spirit burner, and so we have incomplete combustion. You'll be able to tell because you'll have some yellow in your flame, and that's the carbon atoms, and that's that lower heat. Then a blue flame, higher frequency, all of that. You've got a higher heat coming out. Anyway, some incomplete combustion of fuel by method 2 is less exothermic. So you get incomplete combustion is less exothermic. You don't release as much heat, so you're not going to heat the water as much for the same amount of moles that are burnt. So look, there's at least 3 fat marks just for talking about that, the difference with that and that. Let's go on and talk about maybe even 4 just by stating that it's lower. I now want to state that method 3 is also lower than the standard enthalpy for combustion. So oh my God, method 3 is also lower than method 1 because mean bond enthalpies are taken from a range of compounds, okay, not from the liquid hydrocarbon. So what I mean by that is the specific hydrocarbon in this question, the mean bond enthalpies are taken from CC bonds, carbon-carbon bonds from methane, propane, butane, hexane, octane. Maybe this is nonane, this liquid hydrocarbon, but we've been using mean bond enthalpies not from nonane, but from all different other hydrocarbons. So they're not going to be exactly the same. They're affected by the different groups, interactions of electrons, clouds, and things like that. So they're not going to be exactly the same. So that's why this is a little bit out. It's not as out as that because you haven't got all the heat loss, you haven't got all the incomplete combustion, but you have got mean bond enthalpies from a range of different bonds, from a range of compounds. So that's going to get us a mark. So I think we probably got 5 marks here as well by stating that this one is lower and that one is lower as well, and then giving these explanations. But let's hit you with another one. This one is one that people find really hard to understand. But essentially, if I take a hydrocarbon, let's say I take people find this bit difficult to understand. So let's say I take butane. Now, we don't know if that was butane, but it's my liquid hydrocarbon. And I burn it in oxygen. Okay, oxygen's a gas. And I'm going to make carbon dioxide and I'm going to make water. Now, my CO2 is a gas. Often with combustion, you're forming liquid water. What's the problem here? Well, mean bond enthalpies are in the gaseous state. So mean bond enthalpies are taken in gaseous state. Now, what we have to appreciate is that they might not have taken into account the fact that water ends up in the liquid state. So it condenses from H2OG to H2OL. So water goes from H2OG to H2OL. Now, if you are using mean bond enthalpies, why have I put a bracket there? What an idiot. Right. Now, oh my gosh, there we go. Lovely jubbly. So it's not that the water is changing state during this that I'm worried about. It's that the values I've been given to calculate the mean bond enthalpies, you'll often get a table of CC bonds, CH bonds, and they'll all give them to you in a table, and they're mean bond enthalpies that you've been given. They have all been taken in the gaseous state. And here what we have is a difference between the gaseous and the water state. And it's like minus, is it going to be exothermic? If we're going from gas high energy to lower energy, it's going to release energy. It's going to be exothermic. So it's endothermic when you go liquid to gas because you're putting the energy into a higher state. Your gaseous particles have more kinetic energy, so that would be positive. But when we're going from a gaseous state to a liquid state, it'd be something like minus 40, I don't know, kilojoule per mole. For condensation, and this would be the enthalpy of condensation. So enough of my whiffle waffle waffle. What I need to do here is say they haven't taken into account the enthalpy of condensation. For mean bond enthalpies, they are calculated in the gaseous. I love that word gaseous, and rather than gaseous. Right, the gaseous state. So mean, oh, not mean. What are we saying? So enthalpy of condensation needs to be factored in for water. So when you're doing the overall equation, you would need to take into account this, and it would change this number a little bit. And there we go. So you've got to take into account the enthalpy of condensation of water, because in our equation, water is going to be in the liquid state, but the mean bond enthalpies, they broke the bonds in water in the gaseous state. Okay, boom. Let's move on. That's 5 marks. Actually, that's the end of the test. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. I'll see you on the next video. What I want to say is, listen, hit the like, people. I need more likes. Yeah, because I'm desperate. And that's just the way it is. That's just the way it is. Right, bye.
You're still here? It's over.